In a previous DSEM demo video, I showed how to use Mplus to specify a single subject or n=1 time series model. And in this video, I follow up on this and show how to relate the parameter estimates that we get from the analysis in Mplus back to the actual model that we specified. I'm making use of a hypothetical example, so based on simulated data, consisting of daily diary measures where the first variable is how close do you feel to your partner right now? And the second one is how much tension was there in your relationship today. The model we specified in the end was a model in which we have lagged versions of both variables. So we get closeness and tension yesterday. And this was then the model that was actually specified, which could be represented as this path diagram or written as these regression equations. So closeness is regressed on itself. So that's the autoregression. You see that over here. And also on tension at the same occasion, so within the same day. So it's this part. And then tension was regressed on tension at the previous occasion, so yesterday. So that's this autoregression here. And there was a cross-regression, cross-lagged regression from closeness yesterday to tension today. When you look at the parameter estimates for this model, you see that we get a lot of information that's related to doing Bayesian analysis. So what we will see is we get a column with the parameter estimates, so that's the point estimates. Then the second column contains the posterior standard deviation. This is sometimes compared to the frequentist standard error. I don't want to offend the Bayesians here. The third column is the one-tailed p-value. I always skip this column. The part that is really important, though, is this part where we have the 95% credibility interval. So we get a lower bound and an upper bound. And what to look for is whether 0 is inside this interval or not. So if 0 is inside this interval, which is the case, for instance, over here, then we will say, well, there's not a lot of evidence that this parameter really differs from 0. Whereas if 0 is not in this interval, as is the case over here, for instance, then we could say, well, we have evidence that this parameter actually differs from 0. You can also quickly see this by just looking at the column with significance where there's an asterisk when 0 is not inside the credibility interval. And there's no asterisk when 0 is inside the interval. So let's look at how the parameter estimates are then related actually to the parameters that we see here in the path diagram, but also in the regression equation. If we look at the first part, it's about closeness being the dependent variable, and there's two predictors, closeness at the previous occasion and tension. And we see those two parameter estimates here, and we can include them in our path diagram like this. So we have the autoregression, which is positive, so it means if this person felt a lot of closeness yesterday, they probably also feel closeness today. If they felt very little closeness, they probably also feel little closeness today. And there is a negative cross-regression here, so from tension to closeness. So when this person felt a lot of tension in the relationship today, they feel less close to their partner right now, and vice versa. If they experience very little tension, then they feel more close. We can also include these same parameter estimates in the regression equation. So here we have the first regression equation is for closeness as the dependent variable. And so we include the autoregressive parameter and the cross-regression parameter in the regression equation like this. The second part of the parameter estimates is about tension being the dependent variable. So again, we can include these parameter estimates in our path diagram. So we have this cross-lagged effect and we have the autoregressive effect. We can also include these numbers over here in our regression equation for tension. So the autoregressive effect and the cross-lagged effect. Remember though that this one had a credibility interval that contains 0, so we would not try to interpret this parameter in substantive terms. But we do see that there is carryover from tension yesterday to tension today. The third part is about the intercepts. We don't see the intercepts in the in the path diagram, but we do see them in our regression equation. You see them over here. These are the intercepts. And it's the values that we expect for the outcome variables if all the predictors have a mean or have a value of 0. And this might not be a very sensible thing to think about, because it might not even be possible to have a value of 0 on, for instance, closeness or tension. But nevertheless, it is a parameter that's estimated, and they end up here in our regression equations, the tension, the intercept for tension and the intercept for closeness. And finally, we have the residual variances, and this is sometimes a bit tricky to see how this relates to the path diagram, because the path diagram is actually not entirely complete. We have the residuals here, but we have not actually drawn in the residuals. So if we would complete the picture, we would have to draw in the residuals. So these are the zetas that we also see here in the regression equations. And they are variables. They take on a different value at each time point t. And what we estimate is not these residuals, but what we estimate is their variances, and that's indicated by these two-headed arrows of a variable to itself. So we see the residual variance here for closeness. It's the variance of this residual of closeness, zeta CL, and that's this value that we see in the output. And similarly for tension. Now we cannot include these parameter estimates here, because here we have the residuals, not the variances, but we can add information about this. For instance, in this way, where we say the residuals of closeness come from a normal distribution with a mean of 0, because it's residuals, by definition they have a mean of 0. And this is the standard deviation, it's the square root of the variance. And the same thing holds for the residual of tension. It comes from a normal distribution with a mean of 0, and then we take the square root of the variance, the residual variance, for tension. So this is one way to do it. The other way to do it would be to say that these residuals actually come from a multivariate normal distribution. So not two separate normal distributions, but one multivariate normal distribution with a vector of zeros as the mean vector, and then this as the covariance matrix. So now we really do need the variances here. They are on the diagonal. And this would be the covariance between the residuals. And that's set to 0 in this case. It would be a two-headed arrow here between the residuals, but that's not included in our model. And that's the same as saying it's equal to 0. Okay, that's it for this part, the single subject parameter estimates. And we can now go on to specify models for a multi-level version of this. So if we have this kind of data of multiple subjects, we want to specify a model that includes both the time series part, but also the individual differences in certain parameters. And that's what we'll see in another video.